All right, so quantum numbers. Quantum numbers are the definition, like think of them as being like the coordinates of an electron in an atom. Okay, so it's just another way to describe an electron's position in an atom. All right. Let me talk first about what the different quantum numbers are, define them, and give some examples, and then we'll do a couple practice problems. Okay? Think of it in terms of like orbital diagrams, where we have the broadest location of an electron would be the energy level, right? So that's our first quantum number, and that gets the letter N, which you've seen before. N is the official name of it is the principal. Principal. My pen is skipping. And I honestly can't remember if it's supposed to be LE or AL. It's AL. Is it LE? No, I think it's AL because it's the first quantum number. So it's principal as in the first. LE? I'm not an English teacher.
Okay.
But I'm pretty sure it's principal. Like principal. Anyway. So, like I said, that's the official name of it. Or you can just say it's the energy level number. Okay. It's the energy level number. So what are some examples of N? 4, 2, 3, 1, 7, 6. So anywhere from 1 to 7, right? An integer from 1 to 7. Good. Yay. I'll do blue. We actually could go beyond 7. We just don't have any atoms that have more than 7 energy levels. Okay, but theoretically, it's an infinite number. Okay. All right, our second quantum number. So like the next, so energy levels. What are they divided into? Sublevels. So the sublevel gets a quantum number as well, and its symbol is L. And the actual definition of this is the angular momentum quantum number. This is all physics. And I'm going to start abbreviating quantum number because I don't want to write that out multiple times. So that's the official name of it. Its nickname is the sublevel quantum number. Or the sublevel number. Okay. What are our sublevels? S, P, D, and F. But what are these things called that we're talking about? Quantum numbers. We just wrote letters down. So they assign numbers to each of these sublevels. S is 0, P is 1, D is 2, F is 3. Okay. So theoretically, L can be anything from 0 up to n minus 1. Okay? So when you're in, like, for example, the second energy level, the only thing that L can be would be 0 or 1. And let's think about that. On the second energy level, there's only room for the S sublevel and the P sublevel. S is 0, P is 1. There's no D and sublevel on the second energy level. On the third energy level, it's only S, P, and D. What's 3 minus 1? 2. The highest the sublevel number could be for energy level 3 is 2, which corresponds to the D sublevel. Okay? All right. Our third quantum number is m sub L, and this official name is the magnetic quantum number. Its nickname is the orbital number. Remember, sublevels are divided into orbitals. And depending upon the sublevel, you're going to have different numbers of orbitals. Our possible numbers for m sub L is going to be whatever, it's dependent upon what L is, because it's dependent upon what sublevel you're in. So ml will be anything from negative L to positive L. And this will probably, ml is probably the hardest to understand and get, but once we do examples, it'll become clearer. Okay? And then the fourth sublevel, or not sublevel, the fourth quantum number is m sub s. And this one's official name isn't as like funky as the other ones. It's the electron spin quantum number, which I don't have like a nickname for it because the name of it kind of makes sense. This one's going to tell you if it has upspin or downspin, or clockwise spin or counterclockwise spin. Upspin, when we draw an orbital diagram, when we draw the arrow pointing up, that electron we say is spinning clockwise. When we have the arrow drawing down, it's spinning counterclockwise. So it just tells you the direction of spin for that electron. There's only two possible numbers for this quantum number, and that is plus 1/2 or minus 1/2. Plus 1/2 is what type of spin, do you think? Up. Or if we draw it how I draw it in orbital diagrams, meh. That little half arrow because they're faster. And then negative 1/2 is down. It'll make more sense once we do an example. Okay? For right now, just write down those definitions and stuff, and then I'm going to, we're going to do some practice problems, okay? Are you guys ready to move on to the next page? All right. Our first practice problem, I need to complete it. I have to draw the orbital diagram. I couldn't do that typing. So we're going to give the 4 quantum numbers for the circled electron in the following orbital diagram. So let me draw out the orbital diagram. All right, so go ahead and copy over that orbital diagram. And we're going to identify N, L, M sub L, and M sub S for that electron. And while you're writing that down, I'm going to pause it because I don't think we need to record the dead air of you guys writing. Okay, so let's start with N. What energy level is that circled electron in? It's in the 3rd energy level. Okay. What is its L? 2, because it's in the D sublevel, L is 2. ML, this is, like I said, this is the one that's the hardest to understand. Remember, ML is going to be anywhere from negative L to positive L. So our possible numbers for ML would be negative 2 up to positive 2. The way that they get numbered, so from negative 2 to positive 2, how many individual numbers are there? 5. Negative 2, negative 1, 0, plus 1, plus 2. How many orbitals are there? 5. So this one is -2. This one's -1. This one is 0. This one's +1, +2. See how that worked? So what orbital is this electron in? The -1 orbital. And then MS is probably the easiest one because you just look at the direction the arrow is going and it is pointing down. So what is the M sub S? -1/2. People are just having a very loud conversation right outside. Okay, questions on that? All right, our next problem is going to be more like what you're going to see in your homework or, I don't know, on like a multiple choice question. The quantum numbers are great in multiple choice type questions, okay? So this one, we're saying which of the following sets of quantum numbers would not exist or would not be allowed? And then make corrections if needed. One thing I want to point out, this question here is not a multiple choice question. We're going to look at each set and say if it's allowed or not, and then if it's not allowed, figure out where it's wrong and what it needs to be in order to make it allowed. Okay? Bless you. So looking at A. Is anything wrong with A? If so, what is it? Or I guess I should say, would A exist? Yep, A is perfectly allowed. L has to be, remember, L has to be less than N, and then ML has to be within the range of -L to +L. So yep, everything's good. All right, what about B? No, B would not exist. Something's wrong with B. What part of B is wrong? The ML. Remember, ML has to be, for this case, has to be -3 to +3, somewhere within that range. And 4 is outside that range. What about C? What do you think? Yeah, this one isn't allowed either. And it's because of this part right here. N has to be 1 to 7. Can't be 0. Has to be at least 1. And also think about it this way. Electrons have to be on an energy level. If the energy level is 0, that's like the nucleus. And that's not where electrons are. All right, and D, what's wrong with it? Is anything wrong with it? Was that a trick question? What's wrong with L? Yeah, L can't be negative. ML can be negative, but that's the only, like, ML and MS are the only ones that could have negative values. So think M's are the only ones that are allowed to be negative. N and L can't be. Okay, so L, in this case, because N is 2, L can only be 0 or 1. Because N is 2. In order for it to fit with the ML, L would have to be 1. Otherwise, ML would also be wrong. Yes, ma'am. Yeah, if it's a multiple choice, there will only be one right answer. Yeah, but I pulled this question from the textbook problems. So this is going to be more like what you're going to see in your homework. Okay? All right, so that's it that I'm going to talk about with quantum numbers. We're now going to talk about periodic trends. Okay? Back in first year chem, regardless if you took academic or research, when you talked about periodic trends, you pretty much only had to state, like you had to, from like a list of a set of atoms, which one would be like bigger or which one would have the higher ionization energy or something like that. In AP Chem, you not only have to figure that out, but you have to be able to explain why the trend is what it is. And there are some exceptions we're going to talk about. But let's start off just talking about some of the trends. We're going to start with atomic size, with these ones. So 14 and 15 are discussing the size of the atom, or the radius of the atom. In general, what is the overall trend for atomic size? It does go, yes, as you go down on the periodic table, it gets bigger. And what's the direction for the horizontal part? To the left. And we're going to explain why. So yeah, and those arrows are in direction of increasing size. So it increases as you move to the left and down. So we can answer 14 and 15, at least the which one is, and then we'll talk about the why. So based off of the trend arrows, between Na and Cl, which one would be our larger atom? Na. Again, we'll discuss why in just a little bit. And between Li and Cs, which one would be bigger? Cs. All right. Maybe get out your own periodic table. Aw. Do you have your lab notebook? Oh, because there's one in the lab notebook. There's one in the agenda. Yep, there's one in the Briarwoods agenda. Like the, no, not the one I print for you, but like the orange, the little agenda. Oh, you just came unprepared to class. Okay. Oh. Okay, so for this, for the Y, notice how sodium and chlorine, they're in the same period. So the reason why sodium is bigger than chlorine is going to be explained with the horizontal trend, okay? So I'll explain what this means in just a moment, but anytime you're describing, when you're comparing two atoms that are in the same period, the explanation for the trend, whatever the trend is, the explanation for the trend will be something called Zeph. And I'll explain what that means. Zeph stands for effective nuclear charge. And it is calculated by taking the number of protons and subtracting the core electrons. Before we explain more about what Zeph does, let's do just a couple practice problems of calculating the Zeph for different atoms. For example, sodium. How many protons does sodium have? 11. And how many core electrons? Now, core electrons are all the electrons except the valence electrons. Sodium has 10 core electrons because it only has one valence. And 11 minus 1 is 10. So what is 11 minus 10? 1. So sodium's Zeph is 1. Its effective nuclear charge is fairly low. What about boron? Boron. How many protons does it have? 5. And what is its core, how many core electrons does it have? 2. So what is its Zeph? 3. So a higher Zeph, a higher effective nuclear charge than boron. And I'll explain in just a moment what Zeph does. If you haven't already figured out, the easiest way to figure out the core electrons is look for the noble gas that comes right before that atom, because that would be the number of core electrons. All right, what about chlorine? How many protons? 17. And it has how many core electrons? 10. The same number as sodium. What's its Zeph? 7. Are you also noticing that, yeah, the Zeph is basically the number of valence electrons? That's going to be true for all of our representative elements, our group 1 and 2, and then 13 through 18. It's the transition metals that they do slightly different stuff because they're special, okay? So what Zeph means is, so it's nuclear charge. So the charge from the nucleus, the strength of the nucleus that's effective on the valence electrons. So sodium has a much lower effective nuclear charge than chlorine. So chlorine, since it has a much higher effective nuclear charge, it's going to pull on the valence electrons much more. Those valence electrons are going to feel a much greater pull from the nucleus. Whereas in sodium, the valence electrons are not going to feel as much pull from the nucleus because the nucleus only has an effective strength of 1 versus the effective strength of 7 for chlorine. So for here, let me write that down. So sodium oh wait, I meant to write the word Y. I'm explaining the Y here. So since the valence electrons are not going to be pulled in as tightly, the atom will be bigger. So for all of the trends we're going to talk about, whether it's atomic size or ionization energy or whatever, if you're comparing two atoms that are in the same period, but different groups, the explanation for why they're different is going to come down to effective nuclear charge. 15, we're comparing lithium and cesium. They're in the same period. They're in the same group. So their Zeph is going to be the same. Both of them, their Zeph is 1. So the reason for the difference here is not effective nuclear charge. So the vertical trend explanation bless you, is going to be something called shielding. Okay? It's going to be shielding. Shielding is the more core electrons the atom has, the more shielding the valence electrons experience from the nucleus. Shielding meaning that if there's more core electrons, they are shielding the nucleus from the valence electrons. So those valence electrons are going to feel less pull from the nucleus because they're being shielded. Also, another way to think about it is as you move down the periodic table, you're adding energy levels. Think of it as adding layers to the atom, adding shells, it's getting bigger. Okay? So shielding is going to be, so more core electrons, more shielding of okay. So cesium has a lot more core electrons. Cesium has 54 core electrons and lithium has 2. Okay, so cesium is going to be a much larger atom. Okay? So yeah, whenever you're comparing two atoms that are in the same group, then they are going, the reason is because of shielding. When they're in the same period, it's Zeph. So think the horizontal is Zeph, vertical is shielding. Horizontal has a Z in it, which Zeph starts with that same letter. So that's the way to remember it. Horizontal is Zeph. Okay? I'm sorry, what? Just the Y. This is just an aside. The fact that the horizontal trend explanation is always going to be Zeph. Okay? Cool. All right. The next thing we're going to talk about are some of the exceptions, some of the big exceptions to ionization energy. There's always going to be anomalies in the periodic table. There's always going to be random anomalies, meaning like certain elements don't fit the trend. But there are two big exception pieces in ionization energy that's not just specific to an individual atom, it's actually groups. Okay? Before we talk about that, what is ionization energy? Exactly. It's the energy it takes to remove the first electron from an atom, or the most loosely held electron from an atom. The less energy it takes, that means it's the easier to remove. If it takes a lot of energy, it's really difficult to remove. The overall trend to ionization energy is opposite that of size. It's up and to the right. That's our overall trend. And think about that. The smaller the atom, the more tightly held in the valence electrons are, the more difficult it's going to be to remove those valence electrons, so the greater the energy. Okay? Like I said, there are two big exceptions. Two big exceptions, and we're going to explain them. The first exception, and just so you're aware, I'll pretty much fill up my board here. The space on your paper, I pretty much filled it up. So budget your space. Okay? The first big trend that we're going to talk about, or the exception to the trend, is the group 1516 exception, or anomaly. Okay. Based off of the overall trend, elements in group 16 should have a higher ionization energy than elements in group 15. But because this is an exception, you can kind of predict what I'm going to say, that it's really the opposite. Okay? I'm going to use nitrogen and oxygen as my examples because, we only have to deal with a little bit of electrons there. So nitrogen. Its orbital diagram, we'll just do the valence orbital diagram, is 2s with 2 electrons and then 2p with 3 electrons. 1, 1, 1. And then oxygen is the same but with 1 more electron. Like that. So the expectation, and I'm going to start writing smaller because I've already written too big. Expected is that oxygen's ionization energy will be larger than nitrogen's ionization energy. Reality, not the same. Reality is the opposite. And the reason why is because that electron, now, okay, let me back up. The electron in oxygen, the most loosely held electron in oxygen, the first one we would remove would be this down arrow electron. In nitrogen, the first one we would remove would be one of the ones in the p orbitals. It doesn't matter which one, but we typically just would take off the last one we wrote. So, in reality, that electron in oxygen is being repelled. I almost said repaired. I meant to say repelled. It's being repelled by that paired electron. So it's slightly easier to remove than the electron in nitrogen. And also, remember how we talked about the exceptions with electron configurations last class with like chromium and copper groups? How it's a little bit more stable to do a half-filled sublevel than to do only a partially filled. That nitrogen orbital diagram just a little bit more stable. It's a little more happy, okay? So let me write that down. Because the electron in oxygen is being repelled by the paired electron, so it's slightly easier to remove than the in nitrogen. The other big area where there's an exception to the overall trend is group 2 and 13. So based off of the overall trend, elements in group 13 should have a higher ionization energy than elements in group 2. But really it's the opposite, okay? And I'm going to use boron and beryllium as my examples for this one. So Be is just 2s with 2 electrons. Boron is 2s with 2, and then 2p with 1. Okay. So the last electron, or the most loosely held electron in beryllium is typically the last one we draw. So we would be removing that electron, and in boron we would be removing this one. Right? So, expected, write that down, expected borons will be larger than berylliums, i.e. And reality, like I said, is the opposite. And the reason comes down to the type of orbital that the electron is in. So, that p orbital that boron's last electron is in has a more complex shape than the s orbital that beryllium's last electron is in. And because of that complex shape, there are times when the electron in boron, in that p orbital, is going to be farther away from the nucleus than the electrons in the s orbital, which makes it a little bit easier to pluck off. Okay, let me draw those two orbitals. So we have the nucleus, and then there's the 1s orbital that's there, but on top of that, or surrounding that, is going to be the 2s orbital. Superimposed on that, because these are all existing, like, they're kind of like going around the nucleus. Superimposed on that is going to be our p orbitals. I'm only going to draw one of them because it makes a little bit more sense. But that p orbital is kind of superimposed. Remember, that has kind of like a dumbbell shape. So there will be times when that electron is like out here, which is farther away from the nucleus than that s orbital. Not all the time, but there will be times when it is. That's what makes it easier to remove. Okay? So let me write that down. So because the p orbital has a more complex shape than the s orbital. So at times that 1p electron, not saying 1p as an energy level and sublevel, saying like that one electron in the p orbital, that 1p electron is farther from the nucleus so slightly easier to remove. All right? Those are like the big exceptions we're going to talk about. All right, we're going to do more practice. So when you're done writing that down, we're going to turn the page and go on to 17. Are you guys ready? Are you ready? Okay. All right. So no, wait. It's going to be on the last page. It's going to be more like the questions you're going to see in the free response. But okay, let's just continue in practice. So 17, which atom would require more energy to remove the most loosely held electron and why? So figuring out which one, that's Chem 1. That's, baby chem or research chem. Like that's, what do we call it? Baby chem plus? That's stuff you should already know how to do. So basically it's asking which one has a higher ionization energy. That was not a rhetorical question. Chlorine. Sorry. Chlorine would have the higher ionization energy. It would take more energy to remove that, the most loosely held electron, to remove an electron. Between lithium and cesium, which one has a higher ionization energy? Lithium. Because remember, the overall trend for ionization energy is up and to the right. And none of these examples were within our exception. Okay? We would use Zeph to explain the first one because, remember, for all trends, the reason across a period, the reason for the horizontal difference is Zeph. Exactly. So, chlorine has a larger Zeph. Therefore, those electrons are held tighter. So it requires more energy to remove it. And what would we use to explain between lithium and cesium? Shielding, exactly. Lithium has more or less shielding? Less. This is where it's like a little weird. The more shielding you have, the looser the electrons are held. Okay, so this has less shielding. Therefore, the electrons are held tighter. Okay. Yeah, because their Zephs are the same, so it cannot be Zeph. That's the explanation. And for sodium and chlorine, the shielding's the same because they're both in the same period. They're both at the same energy level. So the shielding is the same for for sodium and chlorine. So it has to be Zeph to be the explanation. Okay? All right, moving on. Which one has the larger second ionization energy and why? So we have lithium and beryllium. Orbital diagrams, back in first year chem, you were probably asked just to draw orbital diagrams, and that was pretty much it. Orbital diagrams are great for explaining things like trends. Okay? So let's draw out the orbital diagrams for both of these. And we're going to do the full orbital diagrams, which isn't a big deal because we're looking at 3 and 4 electrons. I think you can handle that. So for lithium, what does its orbital diagram look like? 1s with how many electrons? And then 2s with 1. Good. Beryllium, what does its orbital diagram look like? Yeah, it looks like just like lithium, but with 1 more electron. Exactly. I don't think it was much. I don't think I was asking much of you to draw those orbital diagrams. I could ask you for lead, which might make you happy or sad. Probably sad. All right. In lithium, so let me back up. This question is asking which one basically is going to require more energy to remove the second electron. Let's talk about the first electron first. In lithium, what is the first electron that we're going to remove? The one in the 2s, right? And then once that's gone, what would our second electron be? One of them in the 1s. It doesn't matter which one, but we typically just go in reverse order of how we wrote it. In beryllium, what would be our first electron that we remove? One of them from the 2s, and our second one would be the other one in the 2s. All right. Classify for me the first electron that is removed in lithium. How would you describe that electron? It's a valence electron. And the second electron is what type of electron? Core. In beryllium, describe for me its first electron. Valence. Describe for me its second electron. It's also valence. So, have we answered the question? No, we haven't. We haven't decided which one's going to have a larger second ionization energy. Which one has a larger second ionization energy? Which one do you think?
Lithium.
Lithium. Why? Exactly. It takes more energy to remove a core electron than it does to remove a valence electron. Okay? So let me write that out. Removal of the second electron in lithium is removing a core electron. Therefore, much more energy is required. It's not going to apply to the problem, though. Okay? Questions on this? All right. Why don't you guys answer this one in your pods, and then we'll come back together to go over it. All right, so you've had time to go over this. So ionization energy, what's the overall trend for ionization energy? Up and to the right. Up and to the right. And then for atomic size, what's our overall trend? Or to the left and down, however you want to say it. All right, oxygen, fluorine, and sulfur. Oxygen and sulfur are in group 16. Fluorine is in group 17. So we are not dealing with the weird exceptions within ionization energy, because we're not comparing like a 15, 16, and 17. We're comparing two 16s and a 17. So, ionization energy. Which of these atoms, oxygen, fluorine, and sulfur, will have, we're going increasing ionization energy, so which one's going to be the lowest? Sulfur, good. Then oxygen, then fluorine, yay. And then atomic size, we're going increasing atomic size, so which of these atoms will be the smallest? Fluorine, then oxygen, then sulfur. See, the bigger the atom, the lower the ionization energy, and vice versa. Cool? Yay. On the back, number 21. These are going to be more like our free response questions, okay? Honestly, number 20 was like totally like, I'm pretty sure this question is in the Chem 1 textbook. So like this was easy, or should have been. So instead of, like in free response questions, instead of you identifying which one's going to be the largest or smallest or whatever, it's going to be more like this, where it's going to tell you what it is and you have to explain why. Okay? So why don't you guys take a few minutes to go through 21A, B, and C. We'll come back together for D. Like we'll do D together, but take a few minutes to do A, B, and C. Okay, so why is the atomic radius of magnesium smaller than barium? Because, exactly, barium has more shielding, or actually, since it's specifically referencing magnesium first, magnesium is smaller than barium, there is less shielding in magnesium. Therefore, let me back up. For these types of questions, when you're answering them, make sure you reference both atoms, okay? There's less shielding in magnesium than barium. Therefore, the electrons in magnesium are held tighter than in barium. So the Mg atom is smaller. Okay? In order to get full credit on a lot of these free response questions where it's asking a comparison, you have to mention both. If you just mention one, it's not a complete enough answer. Okay? Ready for B? All right, and I'm telling you this now. On your Unit 9 test, if you see anything that you think it's a typo in terms of trends, I promise you I didn't make any typos. It might be an exception. Like this one, we expect phosphorus to have a lower ionization energy than sulfur, but really it's the other way around. You have to explain why, okay? So why is the ionization energy of sulfur lower than that of phosphorus? Okay, well, if you just say it's because of the 15-16 exception, it's not enough. Yeah, you have to say something along the lines of the electron in sulfur that's being pulled off is experiencing those repelling forces, which makes it slightly easier to remove. Okay, so what I would do, if I were answering this question on an AP test, I would kind of give the ending orbital diagram for both of them, kind of like we did before. So, and then I would say the last electron in sulfur is experiencing repelling forces, which makes it slightly easier to remove compared to the last electron in phosphorus. Okay?
Can you also say the other explanation that a hot filled shell is kind of more stable?
So the only reason I don't want you to use that is because, wait, no, that wouldn't apply. Sorry, I was thinking about if it was 2p2, but 2p2 has a lower ionization energy than 2p3, and that follows the trend. Trying to think. So, group 15 fits the trend. It's 16 that's outside the trend. If you actually were to graph these, you would see here would be group, 13, 14, 15, and then 16 is down, and then 17 goes back up. So it's 16 that's the anomaly, really. So this is why we talk about what's happening in those group 16 elements, not the group 15 elements. Okay? Yeah, it's 16 that's the oddball. Okay? I'm going to erase this because I think I'm going to save this one, and that would be very confusing. I have no eraser. There we go. All right. Next one. The energy required to remove the fourth electron in aluminum is significantly larger than the third electron. Why? Okay, so why is the energy required to remove the fourth significantly larger? Because it's what type of electron? No. It's a core electron. The fact that it's a core electron is the number one reason. Okay? So, if I were answering this question on an AP test, I would draw out the orbital diagram for aluminum, or at least showing the last little bit. So, we had, actually, maybe not even the orbital diagram, maybe just give the electron configuration, 3s2, 3p1. Anything before that is going to be core. So those are my first three electrons. So the fourth electron removed the fact that it's a core electron, we like to see the word core electron, okay? So the fact that it's a core electron, which requires tons more energy. You could then go on to say the core electron, which is closer to the nucleus, therefore more difficult to remove, but make sure you identify it as being the removing of a core electron. Okay? All right, and then the last one I said we were going to do together because it's actually talking about something we have not gone over, which we're going to do very quickly because we're almost out of time. So, briefly explain these. So the energy change associated with gaining an electron, which is called electron affinity, is positive for some atoms and negative for others. So the reason why is some atoms have to be forced to accept an electron, which would give a positive electron affinity. Which would give a positive electron affinity. They'd be endothermic. Okay? It doesn't want to happen. So you have to make it happen. Whereas some atoms readily accept an electron. So they're going to release energy, which would be a negative electron affinity. So this would be exothermic. Right? Exo is better. The types of atoms that are going to have a positive electron affinity are going to be the ones that like to form cations. What types of elements like to form cations? Metals. So metals are going to have more positive electron affinities, and then the atoms that are going to have negative electron affinities are going to be the ones that like to form anions, which are called nonmetals. So nonmetals are going to have a more negative electron affinity.